Okay, let's get started. Welcome to Cal 3. Everyone can get to Canvas? Everyone knows how to get here? Okay, so we're just going to run through some stuff real quick. Don't want to spend too much time going through all this stuff you can read. So I'll start just with the syllabus, the important things, beginning with my name, if it comes up here. There we go. So my name is Robert D. Giovanni, and I teach full-time here. So I know some of you know that already, but for those of you who don't know me, I do teach full-time. Sometimes you get like an adjunct that's only here part-time. So I'm here full-time, and I'm available to you in a couple of ways. You can contact me via cell phone, and that would be, you're at home, you're working through a problem, you're stuck, or maybe you can't figure out where your mistake is. So you take a picture of the problem, you take a picture of your work, and you send both of those to me through a text, and then I can reply back. I can write on my phone with my little stylus, and there's your mistake, whatever. So just make sure that if you do text me, first time you text me, put your name and what class you're in. That way I know who you are, all right? And then also you can come to my office. And my office hours, today we're Monday, Wednesday. I don't have a whole lot of office hours on Monday, Wednesday. I'm in my office before this class at 11 o'clock, and I'm there all the way until this class starts. So about 2 hours before this class. After this class, I don't really have much time. And then on Tuesday, Thursday, I'm there from 9:30 to 12:45. So that's a big chunk of time there. Hopefully it works into your schedule. If it doesn't, yeah, I don't know what to tell you. But I'm available to you. You can always make an appointment with me on Fridays, but we'll have to just establish that by a phone call or email or something like that. Okay, you do need the book for the class because all your homework assignments are going to come out of this. So you should have, if you took Cal 2 here, same book. And my goal is to finish the book. And I've taught this many times, and we've finished the book every time. So I've never come up short. Hopefully that will be the case again. The topics, blah, 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 you can read through that yourself. Let's get to the grade. It's kind of an unusual way I'm going to determine your grade. Standard grading scale, but this is the part that's a little weird. So if you've read through this, you're probably like, what? Okay, so what I'm going to do is I have 8 mini exams that I will send you home with. Your first one you're going to get today. All right, and I'm going to give you 8 of those throughout the semester, and you have to submit 3 of those. All right. Now, I'm still kind of on the fence of whether or not I will take all 8 and then take your best 3, or if you have to pick. But at the end of the day, I'm only taking a grade on 3 of those 8. All right. Now, the reason why is because these mini exams are time intensive. And they are designed to be problems that go beyond what you see in the book. So you're not going to be able to go to like Chegg or anywhere else to get the answers because I made them so you can't really do that, all right? So they take a lot of time. So you might be, trying to cram for another exam and you just don't have time for this. So, okay, you don't do mini exam 4, right? But you have 8 opportunities to do the exams, all right? So I would try and do this first one, get it out of the way. It's one of the easier ones. So I'll hand them out. It'll have a due date. You turn that in. Understand? And that's going to be 45% of your grade. So that's quite a bit of your grade that you can do at home. Some of the mini exams, I'll tell you, you have to work alone. Sometimes I'll tell you can work together. This first one, I'm allowing you to work together. That's only so you can form some groups. I think the next one I'll ask you to work alone. All right? And that's more of an honor system thing than anything else. All right. Then we only have 2 other exams, midterm and final. And the reason for that is because we just don't have time in this class to take 3 or 4 entire class periods to take tests. So we have a lot of material, kind of like Cal 2 was a lot of material. Cal 3 is the same way. There's a lot of information and it gets really heavy towards the end. Chapter 13 is, it takes a while, all right? And there's a lot, especially the last like 3 sections are super important, but like you're at the end of the semester, you're tired, and so, you know, I want you to see the last section of this book. It's really kind of amazing. So, and then you have a homework binder, which will be turned in at the final only. And that is just you turning in all the homework you've done throughout the semester. And that's 15% of your grade. And if you do the math, I believe this is correct, that there are 110 possible points in the class. So that means that there's like a built-in curve. Or you can look at it like the binder is kind of a free 10 points. Does that make sense? If you don't turn in a binder, then you could still get a, what in the class? A 95, right? Okay, does that make sense? So you don't have to turn the binder in, but it's a free 15 points. And I'm not going to look at every assignment and be like, you skipped through a couple of problems. What I want is for you to leave here with something you can take with you that's like, here's Cal 3. This is what I did Cal 3. You know what I'm saying? So, yeah, any questions on that? If at any point in time you want me to look at your binder to see if it looks good, you know, you can run it by me. You know, maybe after the first or second exam, or maybe after the midterm, you say, hey, this is what I'm doing, you know, I'll take a look at it. Okay, policies, blah, 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 you can read that. The SOBI statement just has to do with living these days and ages, right? Like how crazy things are right now. So you see something that doesn't look right, talk to somebody, right? One of the things that we need to be aware of is that there are certain exit points. Like obviously that door is an exit point. Hey! Why aren't you in here? Just messing with you.
GSA doesn't take you, man.
No. All right. Well, okay. All right.
When they start, let me know.
I'll let you know about that lecture soon. Okay. All right. So anyway, UTSA doesn't take the I don't know.
You don't get Cal 3 for UTSA. I understand.
Yeah, speak with your
Well,
advisor.
it's like a tech or like, I don't know.
Yeah. Well, look, how many of you are like electrical engineering majors? EE or something like that? So you have to take engineering analysis, right?
I'm taking that right
Yeah, you're taking EA1?
now. I'm taking that at UTSA.
Yeah. So,
This will just count as like
yeah, what I always tell people is like engineering analysis is linear algebra combined with linear algebra and differential equations, right? But there's also, if you look at an EA book, there's a lot of vector calculus in it too, which is what we're going to do. So I look at this class as being like a supplement to that. Like, because they just throw you in and start, you know, throwing engineering problems at you. You know what I'm saying? Instead of like you understanding any of the fundamental underlying principles of it. So, okay, let's get back to this. If we need to somehow get out of this room, we have 2 exit points. We have that door and that window, not this one, that window right there. Okay, that goes down to an awning, and then you can get out that way. So just so we know, don't go this one. That's a full 3-story drop on the concrete. All right, yeah, keep going here. So what to expect from the class? Oh, calculators. So I'm going to let you use any calculator you want on the midterm and final, but just be aware you always have to show all your work. So I know that like the TI-89, the Nspires can do integration and differentiation and all that, but you still need to show me your work. You can use it to check your work, but I need to see that you can get to the answer, all right? Attendance, yeah, be here. And then I'm going to record all the lectures and post them on YouTube, and they'll go up on YouTube after class. And you can get to those. I'll show you how to get to those. All right, so let's go back to the home page. 10 minutes already. So this will take you to YouTube to watch the videos of what we're doing right now. So if you missed class, before you email me and say, what did I miss? Go here, watch what you missed. Then if you're still confused, you can email me, all right? Then all of your homework assignments, which are given to you on this schedule, which you can download and print out. I would download this and print it and put it somewhere. This shows you for each section. Is this right? Wait a minute. Yeah, that's right. So for each section, it shows you the page and what problems I expect that you would do. All right? Now, I have already created homework solution videos, so for each homework assignment, if you click here, it'll take you to a playlist, and it's me working through all the homework problems. So if you're sitting there doing homework and you get stuck, you can refer to this, and I don't know, is it helpful? You've used it in the past. So it's all here. If you look at some of these, you know, some of these take a while. Like this homework assignment took me about 3 hours to do. Some of them don't take long at all. 30 minutes, right? 38 minutes, 30, that's not too bad. Anyway. Okay, so the homework assignment, the homework solutions are there. So, I mean, really the binder, you should have a binder with homework in it, right? I mean, I'm providing you the answers, so. Class files, you are allowed to print out, where are they? Formulas you can bring to the exams. So if you click on this, you're going to see a lot of formulas here, especially this one. Chapter 13 summary is 16 pages worth of formulas. This is just chapter 13, and it's 16 pages of formulas. And so I don't want you to have to memorize these, so you can bring them to the exam, but you need to print them and bring them. I won't provide them. All right? So you got the files, and then you have your first assignment is due tomorrow. Is that right? Tomorrow at 1 o'clock? Okay, so just click here. It's yes or no. It's basically you signing off on the syllabus, saying I understand the requirements of the course. Done. All right? Any questions? All right. I think that's it for this. I feel like I'm forgetting something. Oh, how we communicate. Sorry. We're going to use this inbox over here. Okay, so officially, all communication has to be done through here. Don't send me an email through your Gmail account or Yahoo account. It's not official that way. It has to be through here. So if something happens, you miss the midterm, you know, you had car problems or something, email me through here, all right? Communicate with me. I did forget something. Now I remember. It's my favorite policy. Here we go. Where is it? Is it not here? Oh my goodness, did I not put it in here? There we go. Electronic devices policy. You may use a laptop or tablet to view the lecture notes. So I'm going to be going through notes the whole semester. I have notes for every section we do. I'm going to be going through them. You have access to them. I saw you had them on your little tablet over there. So you're free to do that. But if I walk around and you're on Tinder, what? I don't know. I don't know what you'd be on, right? You're sitting there, you're playing some game on your laptop, or if you're on your phone, you're texting people, or whatever it is, right? There's a huge penalty for that. 10% off your next exam, which would be the midterm in this case. And that would be for each offense. So basically, I want you to just disconnect from the world, if possible, for an hour and 40 minutes. If you have to take a call or you have something important, just take it outside in the hallway. That's all I ask, okay? We good on that? All right. Same thing with sleeping. I'm not a big fan of sleeping. I am a fan of sleeping, but not in my class. So if you're really tired, miss the class, watch the lecture later, or go in the hallway and take a nap. All right? But try not to, if you feel yourself nodding off in here, just go walk around or something. All right? All right, now I'm done. Y'all seem so quiet. So what have y'all heard about Cal 3? Anything good, anything bad? What have you heard?
I heard that it wasn't that long.
Wasn't?
Don't they do Cal 3 for like a 5-week in the summer?
Well, you can do anything in 5 weeks. You can do Cal 2 in 5 weeks.
That's a lie. I tried that.
Did you try it? I mean, that's what I'm saying. It can be offered, but it's just how much time do you have? I mean, you can't get a degree, you can't get an engineering degree in one semester because there's only so much information you can take in at one time, right? You can't drink water from a fire hose, right? I mean, so you've heard it's less information?
I heard that
Okay. We're going to do chapter 10, 11, 12, and 13. So it's 4 chapters, and it's a lot of material. It really is a lot of material, which is why we only do midterm and final. Anything else you've heard? It's what? It's 3-dimensional? Yeah. Okay. All right. Have you heard whether or not it's easier or harder than Cal 2? You've heard it's easier? You've heard both ways? Okay, so let's just go into this assuming it's harder. Let's just go into it like that, okay? Because I don't necessarily think it's harder. I think that everyone is now at a different level now that they're past Cal 2. So it's relative. Like, had this been what you saw, you know, when you were leaving Cal 1, you would think that this is really hard. But now that you're at a different place, this is going to seem not as hard. But I think the reason why it's not as hard for a lot of people is because we're not really introducing any new technique. Like, we have differentiation and we have integration. That doesn't change. We're not going to add some new thing, you know? So we're still differentiating and integrating. The thing is, we're going to do everything now in 3-dimensional space or 4-dimensional space. And so things start to need to be visualized, and it's harder to do. And that, I think, is what made Cal 3 harder for me as a student, is that we didn't have technology like we have here. So my professor's up there on a chalkboard trying to draw all these 3-dimensional objects, and I'm like, what the hell is he doing, you know? And I couldn't see, he wasn't very good at it, and I couldn't tell what it was, and I'm not blaming it on him. It's hard to draw 3-dimensional space on a flat sheet of paper. It's just hard, okay? So with technology, we can actually visualize things, animate things, move things around, and that's what I've done here. Is I've tried to you know, write up as much as I can in terms of coding using Wolfram Mathematica to give you visualizations of what we're going to be doing. So as long as you can see it and visualize it, I think that this can be somewhat easier than the Cal 2 was. But we'll just see, okay? Should we just start, or do you want kind of like just a general synopsis of what we're going to see throughout the semester? You want synopsis? Who want? Y'all? I think you're outvoted. Sorry. I'll make it pretty brief. All right, and I'm not going to include everything here, but I'll just show you some of the things. Like, you know, Cal 1, we had the basic. I'd say the most fundamental idea in Cal 1 was that if you had some function, we'll just call it f, that we could determine the slope of that tangent line by just taking the derivative, right? And that derivative would create a new function, and then that function would spit out all the slopes along the curve. And then when we get into, and then of course there's a bunch of other stuff in here, right? But, you know, like related rate problems, optimization, all that stuff, like word problems. And then in Cal 2, if you were to kind of like summarize it, you know, you have some function f, you define it on some closed interval like this, and then you can find the area under there. But that requires you have to have the ability to find the antiderivative, and that in itself is problematic, right? There's a lot of different things we have to learn to do that, right? And then you can start playing around. You can say, okay, take this region, rotate it around the x-axis, and you can find a volume, or rotate around the y-axis, find a volume, and then do all this other stuff, right? Yes? So along with that, we could also take just a curve sitting in space, and we could find the length of that curve, right? You find its arc length. Like take it off the paper, stretch it out, how long is it? If we go back to this and wrap it around the x-axis, you get some sort of weird shape like that. Not only could we find the volume of it, we could also find the surface area of it, right? Okay. So in Cal 3, what we're going to do is we're going to think about a new function that doesn't live on a flat sheet of paper anymore. We're going to be looking at a function that lives in 3-dimensional space. So essentially what we're going to have, and we're going to build up to this, is a function that instead of taking a number in and spitting a single number out, it's going to take 2 numbers in and spit 1 number out. So 2 inputs, 1 output. And when we do that, what happens is you need, just like over here, the input was always x, right? And the output was always y. So we just used a flat, xy plane to represent a picture of the function. But if we have two inputs and one output, then we need 3 dimensions to visualize it, right? Does that kind of make sense? Mm-hmm. So what we're going to wind up doing is having x and y be our input, and then our output's going to be z, which is going to be like, if this is the ground, this is going to be, z is going to be up off the ground. And so what we wind up getting, instead of this curve, is we get like a surface, like a floating, like a blanket or something, right? That's just kind of frozen in time. We get this surface sitting in 3-dimensional space. Can you kind of visualize that? And then what we start to do is ask some questions like we did in Cal 1. We say, okay, if you were to give me a point on that surface, just imagine you're standing on this like blanket, right? And then, or maybe you're standing, maybe we take like a little ball and we drop it on that surface and we ask ourselves, which way is it going to roll, right? Well, that has to do with like a slope, doesn't it? But the direction is not as easy as it was back here, right? Because, if I have a curve like that and I drop a ball right here, it's going to roll this way, right? It only has 2 choices, this way or this way. And then the slope of that line is going to basically tell us how fast. But when you're on a surface like this, it could really roll in any direction depending on the surface itself, right? And so it's not going to be as easy for us to find the derivative of a surface. So we'll be investigating that, right? We'll be saying, how do we approach it? Does that make sense? Mm-hmm. Now, here we have this idea of a tangent line, don't we? But here we don't have a tangent line. Instead, we have a tangent plane, and the plane being like a flat sheet of paper. Easiest way I can explain it is if you take let's say a basketball, right? You go to the North Pole of the basketball, you can imagine balancing a cardboard sheet on top of that ball, right? And that would be like a tangent plane. It would touch that ball at just one point at the North Pole. But you could extend that concept to any shape in trying to find that perfect plane that would touch that surface at just one point. Kind of make sense? Okay, so we're going to do that, and we'll mess with that. And then we're going to say, all right, well, kind of like we did in Cal 2, let's imagine dropping straight down like this onto the ground. So let's look at like a little box on the ground. So if you take just the points in here and you plug them up into the surface, you get just that blanket part right there, right? It doesn't keep it extending in every direction. So what I've done is I've kind of constrained the function just like we do in Cal 2. We take a function, we cut it off, and then we find the area. Here, we're going to cut it off somehow, and then we're going to find the volume, okay? Because it's 3-dimensional now. So if we project this thing downward, we have a solid object there, right? And so we're going to want to know what the volume of that is. All right.
Kind of how we can find the length of an arc?
Uh-huh.
Could we find the surface area on the cutoff?
Yes, we can. So we can find the surface area of this, all right? And that'll be, something. There's going to be a lot of things we have to develop first before we can do it. But yes, that'll be one of the things we can answer. And then we start getting into things like, we start to put these surfaces into inside of what we call a vector field. So now you have a surface sitting inside of maybe like a magnetic field. And then you start trying to calculate this thing called flux, where it's like measuring like how much stuff is going through the surface. That requires even more. So that's way off, okay? That's chapter 13, all right? But that's kind of like where we're going to go, all right? We okay with this? This is enough for us to get started? Okay. The big thing is it's mostly 3-dimensional, but there will be times where we have functions that instead of having 2 inputs and 1 output, we could possibly have 3 inputs and 1 output. And then everything falls apart because you can't visualize it anymore, right? If I have 3 inputs and 1 output, then I need 4 dimensions to see it, and I can't do that, right? So it becomes a little challenging. All right, but we start. So these notes, like I said, are in Canvas, and you can download them. I believe they're in a PDF version. Let's check something. if I'm not mistaken, I think I also provided them in what's called CDF. See this right here? So this is, course lecture notes is what I'm showing, well, is that what you have open, the PDF? You did the CDF. So the CDF, tell me if I'm explaining this right. You had to go to Wolfram's website and download a player.
Well, I got a discounted version of Mathematica.
Okay, a student version?
No.
Something like, okay, a discounted version.
Yeah.
Good.
And yeah.
And so you can open them.
Viruses too, but it's okay.
Yeah. So, but you're able to open this because you have a full-blown version, basically, of Mathematica. And I would recommend that if you're all in some sort of engineering field or something, to get your hands on some sort of software to start getting used to using it. I'm a fan of Mathematica because I've been using it since version like 1 point something, you know, and they're way up there at like 10 something. I think it's used quite a bit. If everyone likes Wolfram Alpha, right, the brains behind Wolfram Alpha is Mathematica. So, okay, getting back to this. This right here, CDF, you go to Wolfram website, you download their free player, and then when you open the files, you can do everything that I'm doing here. The only thing you can't do is go in there and edit my code, all right? If you get the full-blown version, I believe you can, right?
Yeah, but I'm not even going to do that.
I don't care. I don't care if you do. In fact, if you're a computer science person, why not go mess with my code? You know, I mean, it's all there for you if you want it. So if you want to be able to interact with the notes the way I'm going to, then download the CDF. If you just want to look at what I'm doing, then you download just the course notes and, have those. Okay, so here we go. 3D coordinate system 10.1. So we'll start off with the first little point here. 10.1.1 means chapter 10, section 1, note number 1. So points in R1. R1 means one-dimensional space, which is just a number line. So if we write down on the board right now, x equals 2, all right? I think we all understand that that represents a point on a line, right? The x-coordinate is 2. It's probably, I'm not going to be able to get to it, but you get the, oh, there we go. There we go. That's x is 2, right? Big deal, right? Big deal. Now, what if I write down x equals 2, but now I'm telling you we're in two-dimensional space? What is it? It's a line now. It's no longer a point because your space is now two-dimensional. So it's very important that if someone says x equals 2 and asks you to plot that, your next question to them should be, what space am I in? If I'm in one-dimensional space, I'm going to plot a point. If I'm in two-dimensional space, this really represents, x equals 2 really means the set of ordered pairs, points in two-dimensional space, where x is 2 and the y-coordinate is what we would consider to be free. Okay, it can be anything we want. So x equals 2 means, look, just the x-coordinate has to be 2, but the y-coordinate can be free. I'll just stop here. That's good enough. Set. So that means that x equals 2. Why am I not? Oh, I know why. I know why. Because I need to go to the next note. There we go. X is 2 and y is free. So there, that vertical line is x equals 2. Now, if I want to specify an actual point, a specific point, then what I'd have to do is write like 2, 4. Now you're actually 2 over 4 up, right? So that's the point 2, 4. But if you just write x equals 2 in two-dimensional space, you've got a vertical line. All right? Is that pretty straightforward? So what if we write y is negative 1? If we're in R2, then what does y equals negative 1 look like? So that will be a horizontal line. Okay, if y is negative 1, there, if y is negative 1, then your x-coordinate is now free. And so y has to be negative 1, but your x can be any value. So it's all those points along that line. Okay. So some other things we should be aware of. Let me do something here. There we go. Some other things we should be aware of in two-dimensional space, lines, when it comes to lines. We can write equations of lines like y equals x. You know, that's our standard identity function, right? Y equals x. And this is the way you would write the ordered pair for that line. Whatever x is, y is, right? They're the same thing. But if you look at the line y equals 3x, that has a slope of 3, then all ordered pairs must satisfy this. Whatever x is, the y coordinate has to be 3 times that. And then, of course, you can do that for any linear equation. If y is this, then all ordered pairs must take on this form. This should all be like putting you to sleep right now. Yes? Okay, but what about now if we go into R3? So for R3, what we have, remember in R2, we have things called ordered pairs. Okay, ordered pairs. That's what a point looked like, right? You gave me an x and a y, and that would be a point in two-dimensional space. But in three-dimensional space, we have an x, a y, and now a third number, z. And so we have a name for this. We don't call it an ordered pair anymore. We call it an ordered, anyone know? Triple. Ordered triple, exactly. An ordered triple. So ordered pair means there was 2, right? Triple means there's 3. What is the word ordered? Why does that have to be there?
This is the order that you.
The order matters, right? I mean, like 2, 4 is not the same as the point 4, 2, right? These are not the same. The order matters. So an ordered pair, this order is important because the first number is always the x, second number is always the y, and in this case, order triple, it's x, y, and then the third number is always your z. So how do we graph ordered triples? Just by a show of hands, how many of you have worked with drawing three-dimensional stuff before? That's it? Just a few? Okay. So this is our standard xy plane, right? This is our standard xy. Here's x, here's y. Now imagine now that there's a z, an axis that's perpendicular to the others that's coming straight out at us, right? Then let me kind of reorient things. Well, let me go back to this. Yeah, oops, I messed it up. I'll just go back to normal. So let's see if that makes sense. Can you all see that visually? You're okay with this idea if I spin this around? What I've basically done is I've taken the xy plane like this with z coming out, and I've turned it like this, and we're now looking at it kind of like that. You'll see that? So my xy plane's kind of laying on the ground, and my z is coming out. So if I want to draw an ordered pair, let's say I want to plot this point, 3, 4, -1, then how could I draw that here? Well, I'd have to go out on the x-axis. I'd have to go on the x-axis, which is this way. I have to go out 3, right? So I'd have to mark out 1, 2, 3. I think that's 3. Can't even tell. Close enough. There's 3, let's say. All right? So there's 3. And then what about on the y-axis? 4. So 4 would be out like this way, right? So I need to move this point this distance, but it has to be parallel to this line. So it would be like this. Do you see how I'm keeping this line parallel to this one? So, but I'm going out this distance. So I'm measuring that, putting it here. So y is going to go out to 4. So that moves that point out to 4-ish. So, all right, that's good enough. And then my z has to go down 1. So that point now needs to move down 1. So a distance of 1 down. And I have to be parallel to the z-axis, so just straight down. -1, something like that. So there it is. There's that point in three-dimensional space. Right? Okay. That's tough to do on a sheet of paper. I mean, like, you try it. It's going to be hard to do. So there is something that I do provide that will help you kind of get started with this. It's called 3D graph paper. I'm going to download it real quick. It's not the best, but here's what, it's got these little grid lines in here. So if I wanted to plot the point 3, 4, -1, here's my x, so I go 1, 2, 3, right? There's 3. And then my y go out 1, 2, 3, 4. So you can see the lines are already here, kind of. So you can just follow that out here. And then you have to go down 1. So 1 unit down from there would be right there. So 1 unit down, there's your point. Okay? But you can't spin it around. So, I mean, it's hard to tell where it is because it's on a flat sheet of paper. So you can use that if you want, print it out and practice plotting points. Okay, so now, question. If I write x equals 2, and we're in R3, what does that look like?
That's going to be a plane.
A plane. And by plane, what we mean in this class, a plane means a flat sheet of paper that extends in every direction forever, all right? So this means that it's all the ordered triples. It's all the ordered triples where 2 is your x-coordinate, but your y and z is free, right? So your y and z can move around, but your x equals 2 always has to be 2. So if I draw that, get this out of here. I'm going to move so my x right now is 2. Let me rotate this so you can see that. Can you all see that my x is 2 on that plane?
Yeah.
So I have to kind of pass through there and you can kind of see it happening. And then my y and my z, notice that this point lies on that plane. My y and z, no matter what I do to it, no matter what I do to that y or that z, I'm still on that plane. So x equals 2 is a plane in R3. Now, what about x equals 0? What would that look like? It'd still be a plane, right? But this is an important plane. X equals 0 is an important plane because it contains both the y-axis and the z-axis are both in that plane, right? Agreed? So the x equals 0, we have a special name for it. It is called the yz plane because it contains the y and the z-axis in it. Do y'all understand that? So the yz plane has as its equation x equals 0. And that's what it looks like. So let's go back to x equals 2. Okay, wherever. X is 2, right? If I were trying to describe that to you, x equals 2, what I could say is I could say x equals 2 is a plane that is parallel, that means pointing in the same direction, right? Parallel to the yz plane. X equals 2 is a plane that is parallel to the yz plane. It's 2 units away from it, right? But it's parallel to it. Now, with this, using this same concept, we can do this for different variables. So what about if I give you the equation y equals 0 in R3? So that's still a plane, right? Your x and z are free this time. So let me bring that plane in here. This time, it runs that way instead. And so if I go to y equals 0, that will contain what in it? What will that plane have inside of it if I go y equals 0? The x and the z-axis this time are in that plane. The x-axis is completely contained. Get out of here. Get out of there. The x and the z-axis are completely contained in that plane, so we'll call it the xz plane. And then, of course, the equation z equals 0 in R3 will be called the xy plane. Yeah? XY plane. Lovely. I don't want to shut that door because we might melt, but that is pretty annoying.
Is it possible to turn the lights on, or does it have to be on?
I was doing that just so you could see. We can try the lights on. You want to try that?
I'm just like nodding off.
Are you?
Well, when the lights are on, yeah, just like.
Let's see. If everyone can still see it, I'll leave it on. Can you all still see that okay? All right, just let me know if it becomes visually difficult. I'm going to just leave this cracked a little bit so we can breathe, but that's going to help. All right, so we've got those common planes down now. We got 3 of them. All right. So just like back in, it was probably, I don't know, college algebra, where we determined, do you remember the quadrants?
Yeah.
Okay, we had quadrants, quad meaning 4, right? And they were labeled quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Why did we do it that way? Why is it labeled like this? Why didn't we do like 1, 2, 3, 4? Does anyone know why we did it? 1, 2, 3, 4? What? Is that what you were going to say?
No, I was actually going to say because that's typically the way that's typically the order in which, if you had a circle on that plane centered at x, centered at the origin, that's typically the way that you would represent the distance around the circle, like radians or degrees.
Okay, so when we were talking about degrees, right? When we talked about degrees back in pre-cal, we always said, okay, we're going to always start pointed out the positive direction, the x-axis, right? And then a positive angle is going to go counterclockwise, and it's going to go here, so that's going to be like, 10 degrees, 20, 30, whatever, and then it's going to go around and then come back, right? So it makes sense that you would want to go through the quadrants in order, right? 1, and then 2, and then 3, and then 4. So that's why we number them that way, all right? Now, if you have a point in quadrant 1, let's say we take this point right here, and it has the ordered pair x, y, we can say that both the x and the y have to be positive, right, to be in the first quadrant? So x and y both have to be greater than 0 if you're in quadrant 1. If you're in quadrant 2, what can you tell me about x and y? X is negative and y is positive. And then you can keep going around doing that, labeling this. Okay, but now we're going to be in 3-dimensional space. So if we're in 3-dimensional space, yeah, I'll get back to that. If we're in 3-dimensional space, then there's a lot of issues here. Like, how do we determine what are we going to call this? We're going to have these different regions. We're going to have 8 of them. Does it make sense that we would have 8 different sections broken up by the coordinate axes? So we call them octants. So let me show you the first octant. The first octant has to have a positive x, a positive y, and a positive z. So all the coordinates in the point have to be positive. So that means you have to go out x positive, y has to be positive, and then z has to be positive. So octant 1 is basically made up of all the points that live within this block, right? That would be your first octant right there. Anything living inside there would be in octant 1. Make sense? Okay, then octant 2 has as its conditions that the x changes to negative, but your y is positive and your z is positive. So that means the only difference between octant 1 and 2 is that this x-coordinate is negative, right? So that means that you've got to be on the back side over here of octant 1. Right? And then we just keep going around. So it's like if the xy plane is the ground, then we had the first octant, second octant, we're going to go around the back side of that, that'll be the third, and then come around the fourth. So let me bring those in here. I'm going to make octant 1 a little smaller. So there's octant 1. Octant 3 is about to appear up here in the back side. There it is. There's octant 3. Octant 4 is right there. So there are your first 4 octants. And all of them have one thing in common. The z is positive. You're above the xy plane. Okay? Then you start with the 5th octant. And the 5th octant lies right below the first octant. So it's right there below it. I don't know why it's doing that. And then you just start wrapping around again. So 6th is going to be there. 7th will be along the back side. It's going to get hard to see all this now. Seventh octant will be down back there, and then the 8th octant will come in through here, like that. Is that pretty clear? Yeah? Okay. So I'm going to reference this corner of the room throughout the semester so that we all have like a good reference point to work off. It's not going to show up on camera, but I'm going to have to do this. So what we need to do now is we need to establish how it is we're going to draw things in this class so that we're all kind of on the same page. Now, if you go back and think about R2, this was the standard way that we labeled our x and y axes, right? And we always knew that this meant the positive direction of x and the positive direction of y. Yes? Now, what happens if someone comes in and they want to be a rebel, right? So they rebel, and they're like, no, I want to change this, and I want to make this my y positive and this my x positive. Then my question to you is, does the math that we do here still work over here? Yes, it does. And the reason why is because the easiest way I can explain it, I think, is to ask you, is there a way to turn this into that if you're allowed to move things around, up, down, left, right, and you're allowed to flip things over? So if I take this picture right here and turn it like this, right? Rotate it, then it would become this. And then what could I do to make it turn into that? Just flip it over the x-axis, right? Reflect it over the x-axis. So if you can somehow transform this into that by using just translations and reflections, then these are what we call isomorphic, and they're the same. The math that happens here is identical to the math that happens here. And it does not matter how someone does this. Like they could get, they could say, okay, I want that to be x positive, right? So then how do you turn this back into this?
Rotate it.
Just turn it, right? So I mean, there's nothing anyone's going to be able to do with two-dimensional space to screw things up, okay? Everything is isomorphic, no matter how you label your axes. But in three-dimensional space, it doesn't work. Like, there are ways that we could have things that are different. So let's try R3. Let's say that I decide, let me show you how I like to draw R3, 2 different ways. I'll draw an X, but it's like a flattened out X. It's been like smashed down. Y'all see that? And then I draw a line straight down through the center, like that. That's one way I do it. There's another way. You go like this, and then like that. That's pretty much just picking up the first octant. So this is X positive, this is Y positive, and this is Z positive. Here, we can do the same thing. X positive, Y positive, Z positive. So that's just 2 different ways to draw a 3-dimensional space. So my question now is, and I've kind of already told you the answer, can somebody label these axes a different way and it be okay? So can someone do this? what if they switch those on us? Then is the math that we do here the same as the math that we would do here? So you have to ask yourself, is there a way to somehow move up, down, left, right, or reflect to get from here back to that? And the answer is no, there's not a way to do it. Okay? So these two spaces are not isomorphic to one another, and therefore the math that you do here, you get different answers than the math that you would do here. Which means that we all had to, at some point, we meaning human beings, had to all agree upon the way we're going to draw three-dimensional space. And the way we agreed upon was by using what we call the right-hand rule. All right? So how many of you have heard of the right-hand rule? Okay, a couple of you. So the right-hand rule works like this. When you're drawing three-dimensional space, you use your right hand to use as a reference, and your fingers, if you point them out the x-axis in the positive direction, okay, so I have my x-axis, wherever it is, okay? If I point my fingers out to the x-axis like this, then my fingers need to curl towards the positive y-axis. All right, that has to happen, and then your thumb has to go out the positive z-axis. So look at this picture right here. If my fingers are pointed down the x-axis, if I curl my fingers, won't that curl towards the positive y-axis? Okay, and my thumb is pointed in the positive z direction, right? So this would qualify as satisfying the right-hand rule. Now look at this one here. Why doesn't this one work? If I put my fingers down the x-axis, right, my fingers don't curl towards the positive y. So in order to make them curl towards the positive y, I'd have to turn my hand over. So now they curl towards the positive y, don't they? But look at my thumb. My thumb is pointed this way, and that's not the positive z direction. That's the positive z direction. So this does not follow the right-hand rule. Make sense? Okay, so let me do this. Pardon?
Oh, no.
You're okay? All right, so what about this? What if I put z plus here and x plus here? Let me extend these out a little bit. So where would I have to put y plus in order for that to satisfy the right-hand rule?
Left side.
Left side? Right here. This would have to be y plus. Because if I point my fingers the x plus direction, curl my fingers towards the y plus direction, then my thumb better be pointed in the z plus direction, which it is. Make sense? Okay, so back to the room. This room now, okay, is going to be the first octant. And this right here is the point 0, 0, 0 at the origin, okay? This is the x-axis, this way. This is the y-axis. When I say x-axis, I mean positive. Y-axis positive. Right-hand rule. Z-axis positive. All right? So if someone said go to the point 1, 7, 0, I would go 1, 1, 2, 3, 4, 5, 6, 7, and I wouldn't go up and down. And I'd be right here. Right? Okay. So that's our reference from here on out. All right? Now, I believe in my Mathematica notes. Let me go to my notes here. Go to my next one. So the right-hand rule is in here in the notes, just to remind you. I skipped over it, but now I'm coming back to it. There's your right-hand rule. There's a picture of it. I have to tell this story. I was taking a class in undergraduate school called Non-Euclidean Geometry, and we had to basically draw things in different spaces. And one of the things I had to do, we had to use the right-hand rule. So I took my answer up to the professor to talk to her about it. And I was like, yeah, you know, this isn't coming out right. I'm not sure what's going on. You know, I'm using the right-hand rule and I'm curling. And she's like, that's your left hand. I'm like, shit. Because I'm left-handed, you know, so it was like, I don't know. So, of course, the right-hand rule, you have to use your right hand. Seems trivial, but some people forget, like me. Okay, right hand. All right, so now we've already talked about surfaces in three-dimensional space. Those planes that we were looking at earlier, those planes, those are all what we consider to be surfaces in three-dimensional space. I don't need to necessarily go through all these again, but these are three examples of surfaces in three-dimensional space. I don't know why I had to, oh, that's so you can see the axes, but there they are. All right. So do you remember in algebra, well, yeah, algebra, we had a formula that said that if you are given 2 points in two-dimensional space, call it x1, y1, and x2, y2, that if you wanted to know the distance between these 2 points, that there was a formula for it?
Yes.
Yep. Anyone remember the formula? x2 minus x1, y2 minus y1, but it's squared and plus and squared and square root. So where does this formula come from? It comes very, very simply from drawing a right triangle. And then saying, okay, well, if that's a right triangle, we know that if we call this side A and this side B, then a squared plus b squared is c squared, right? So I could say a squared plus b squared equals, in this case, I'll call it d squared. That would be your Pythagorean identity. And if I want to solve for d, I just take the square root of both sides, like that. So the square root goes away, or the squared goes away here. And then what is a? Well, a is that distance, right? And that distance is the difference between the x-coordinates. So that's the difference between x2 and x1. So x2 minus x1, that's your a squared. And then plus, and this is your b, is your difference of y-coordinates. Yeah? Okay, so that's the formula in two-dimensional space. In three-dimensional space, we have the same thing. But it's a little more complicated. So I'm going to see if I can, well, there's the formula, all right? So this is the formula. Instead of using x1, y1, z1, and x2, y2, z2, the book uses x, y, z is one of your points. Your other point is RST. And look at the formula. Does that look familiar? Doesn't that look just like that other formula? Yeah, all you've done is added this one little component to it. That's it. It's somewhat amazing that that's what happens. But let me try and explain why, okay? So let's say that I wanted to know the distance from here, we'll just start at the origin, to the projector, okay? So this point here has 3 numbers, right? Here, 0, 0, 0. And then that up there has 3 numbers, whatever they are. Then imagine this picture. Here's the corner of the room. Here's the projector, okay? So there's that point. I'm trying to find the distance between those two right there, that distance. Imagine drawing a right triangle like this, right? So that right triangle would look like this. It would go up to the projector, down to the ground, and back to me, right? Okay, I want to know that hypotenuse. So the hypotenuse that I'm trying to find, I would need to know this side and this side, wouldn't I? Okay, this side right here would simply be the distance from projector to the ground, wouldn't it? So that side right here would be the difference in the z-coordinates, which for us would be z minus t, right? That would be that distance. Agreed? Now, what would this distance be? Yeah, so if I'm trying to go from here to the ground over there, right? Here to the ground, then that distance right there is my difference in x coordinates, right? To get to over there. And this right here is my difference in y coordinates. So you could almost visualize, maybe you can, that this right here is actually the hypotenuse of a right triangle that's on the ground. Do you all see my right triangle?